In our last lesson, we learned about how different factors change the speed or rate that a solute will dissolve, and now we're going to look at how the amount of solute that you add can change the type of solution. So there are three types of solutions that we're going to look at. The first one is an unsaturated solution. Okay, when you have an unsaturated solution, that means the solvent contains less solute than it can hold. These are your underachievers, okay? Black coffee, just plain, has no sugar in it, even though it could dissolve more. Okay, so if you have sugar or a solution and it could dissolve more, it just doesn't have that much in it, then it's an unsaturated solution. A saturated solution is a solution where the solvent contains the maximum amount of solute. Okay, so if you try to add more of your solute to a saturated solution, it does not dissolve. Okay, it stays a solid at the bottom of your cup. Okay, so like for example, one time I went somewhere and they gave me unsweet tea and I tried to put sugar packets. I tried to open it and pour the sugar in, and the sugar just would not dissolve. It stayed a solid and it was very gross. It was grainy and I didn't enjoy it. But one way, let's think, how could I tell if my coffee was saturated or unsaturated? Well, we know that if we just look at the color, right, if there's no milk or anything in it, then the coffee is just black, right? But if I add the sugar to it, which actually I shouldn't really be drawing there, we're going to have to write. But if I add more sugar to it, there's a couple of things that could happen. So let's see, if we add sugar, which is our solute, to the coffee, there are two things that could happen. Either the sugar could dissolve or the sugar will not dissolve. Okay. Now, if it dissolves, that tells us that the solution was unsaturated because it had not already dissolved the maximum. But if it does not dissolve, that means it had already dissolved the maximum, and so it was a saturated solution. It cannot hold any additional solute. Okay. The third type of solution we're going to look at is a super saturated solution. And as you might guess, this is a solution that contains more solute than can normally be held at that temperature. So it's very dependent on temperature. Okay, and this is made a special way. So an example of a super saturated solution is McDonald's sweet tea. If you've ever had it, you know that it is very, very sweet. And if they try to take the amount of sugar that they put into it and put it in cold water, it will not work. They won't be able to make it. But what they do is if you heat up the solution, so if you heat it up, you heat up the solution to dissolve the extra, and then you can cool it slowly to a low temperature, right? You can cool it down slowly to a low temperature. And it's kind of like the sugar gets a little lazy. It's like, I'm already dissolved. Might as well stay dissolved. That's kind of what happens. It's how rock candy is created. It's how sweet tea is created. Typically how you make Kool-Aid if you're putting enough sugar in it, because you'll realize, okay, I can't fit this amount of sugar in the liquid unless it is warm. And then you can cool it down in the refrigerator or with ice, and the sugar will stay dissolved. Now with solubility, okay, solubility is how we measure the amount, okay? So solubility is the amount of a solute which is our substance, that can be dissolved in a fixed amount of solvent at a particular temperature. So we know that the amount I can dissolve is dependent on the temperature, but we also know it's dependent on how much water or solvent we have. If I have a little bit of water, I can only dissolve a little bit of sugar. If I have a large amount of water, I can dissolve a large amount of sugar. You have to have a certain amount of water and a particular temperature. And this can be represented by a solubility graph. This shows the relationship between temperature and the amount of the solute that is dissolved, typically measured in units of grams. Your independent variable, which remember independent variable is IV, okay, this is going to be temperature because that's a thing you can control. I can change the temperature of my water. What I can't change is my dependent variable, and that's our solubility. The only way to force the solubility to change is to change the temperature. It's determined by it. It's dependent on it. So when you have a graph, your independent variable is on our x-axis, that's temperature, and our y-axis has units of grams of solute per 100 grams of water. So what that tells us is, let's say right here is about 50 grams on our chart. What they're telling you with that unit is that you have 50 grams of sugar or whatever your solute is in 100 grams of water. So all they're telling you is how much water they were trying to dissolve it in. Okay, and so what we can see is, let's just roll with the sugar example. This line represents the solubility of sugar at different chemicals or at different temperatures. I'm 100% making up these numbers, so don't quote me on them. Okay, but if we look at 50 grams, okay, and we go all the way to where the line is, and then we are to look at what temperature that's at, let's say that's at 70 degrees Celsius, okay? That means this point, 50 grams of sugar dissolved at 70 degrees Celsius, this would be considered the maximum amount of sugar that can dissolve at 70 degrees Celsius. Okay, that's the maximum amount. Anything less than 50 would be less than the maximum. Above 50 is more than the maximum. So that means any point along the curve is a saturated solution. Okay, this is a saturated solution. So another example of that is, let's say we're not at 70 degrees. Let's say that we are at, I don't know, like 30 degrees. Well, if we were to look at that point, okay, let's say it's about 10 grams, then that point is also saturated. Okay, whether or not you're saturated is very dependent on the temperature that you are looking at, because 10 grams would not be saturated at 70 degrees. Now, let's say what if you still have 70 degrees, but instead you've got this point here. Let's say you're at about 25 grams. This point, so 25 grams at 70 degrees Celsius, that would give us an unsaturated solution because that is less than the maximum. Okay, so that means it's capable of dissolving about 25 more grams to get up to 50. Now, if you have amounts that are above the maximum, it's not always going to be super saturated, so we need to take a look at a couple of key features. So let's say we've got this amount and this amount. So let's say they're both at 70. But let's say this first one is at about 60 grams, and the second one is around, I don't know, 75 grams. The key thing is what they tell you happens to the extra, the more than the maximum. So for the 60 grams, if it says that it's not all dissolved, if they say it's not all dissolved, that means you have a saturated solution. That means it's saturated with about, let's see, 60 to, the difference between 50 and 60 is 10 grams. So that means you would have about 10 grams that's undissolved. That's just extra, sitting at the bottom. Okay? But if they tell you, like this 75 grams, if they tell you they added 75 grams and it's all dissolved, that means it wasn't always at 70 degrees Celsius. It used to be at a higher temperature, and then they've cooled it down. And so that would be a super saturated solution. So the only way to be super saturated is if there's more than the maximum in there and it was all able to dissolve. Okay, so that's the key feature there. So you've got several practice problems here. I'm going to run through the answers in the video. I'm not going to show you how I get them, but I do want you to be able to check your work. So for number 1, you should get about 49 grams or 50. You should have an unsaturated solution for number 2, 90 degrees, cesium sulfate. You need 10 grams, and here you've got 30 grams. So you can check those. I would try them on your own. And then the last thing we want to look at is how we actually create a graph. Okay, one of the things on the gateway you might be asked to do is actually graph for yourself. So your title is often seen as the effect of your independent variable on your dependent variable. And for your lab, for my honor students, you guys have to create graphs for your model. So pay attention to what needs to be in a graph. So you have a title, often seen as the effect of your independent variable on whatever your dependent variable is. Your independent variable is the one that's controlled by the scientist. So this, in the case of solubility, that would be temperature, right? So for us, it's temperature in degrees Celsius on our x-axis. That's our independent variable. Our dependent variable is going to be solubility, because that is what is dependent upon what temperature it is. And then you have a title, and then you need to do your scale. Now your scale is probably the hardest part to do for students. So let's take a look at an example. So if you look at this here, we've got our temperature, which is going to be our x-axis, and our solubility, which is our y-axis, okay? One thing to keep in mind is your scale will always start at 0. So this point here on our graph is 0, 0, bottom left corner, and it needs to be able to fit the largest number. So if we look in temperature, our largest number is 60 degrees. Now we also see that this is in multiples of 10, so we have two options. We can count our boxes. So by the way, there are 20 boxes to the left and 20 boxes up and down. And if we say 60 divided by 20 boxes, what that will give us is 3. So that tells us that each box is 3, and so I can count up by 3, 6, 9, okay, and that will make this very last box 60. That's probably the best way. Counting up by 3s is not as easy, so one thing you can do is you can round up. So instead of 60, you could round to 100, and 100 divided by 20 is 5, so you could count up in multiples of 5s, but you wouldn't want to go higher than that because you want to take up your whole graph. I'm going to count up by 3. So one thing I do is I typically have big handwriting, so if you're doing a graph and you're like 3, 6, 9, and it's like all your numbers are running together, what you can do is number the first one and then skip one and number the second one. So we have 3, 6, 9, and then we have 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 41, 45, let's see, the next one should be 51, and then 57, and then this last one is 60, okay? So we can use that to figure out our scale. Now our scale for our y-axis, the biggest number is 3.4. That's not an easy number to use like 60 was. So one thing that you can do is notice that the largest place is the ones place. So instead of having 3.4, we could round to 4. And so if we say, okay, 4 divided by 20 boxes, Okay, that gives us 0.2. And so that means we can increase by 0.2. So 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6, 1.8, 2.0. Okay, 2.2, 2.4, 2.6, 2.8, 3, 3.2, 3.4, 3.6, 3.8, 4.0. And so that allows us to get very close to 3.4 and still take up a large quantity of our graph, because if you're only using like this portion of your graph, then that's a problem. You need to make your scale a little bigger. Okay, and so what we'll do is we'll take these points and we'll graph their coordinates. So if we have 0 degrees Celsius and 3.4 grams, so remember we need to label ours. So we have temperature in degrees Celsius. That's what we see as being our x-axis there. So we just kind of take the label from our data table. And then on our y-axis, we have solubility, which is our grams of carbon dioxide per kilogram of water. And so 0 and 3.4 grams will be right here. 10 and 2.5 grams. So 10 is a little above 9. 2.5 would be about there. And then we have 20 and 1.7. We got about there. 30 and 1.3. So done those two. 40 and 1. And then 50 and 0.8. And then 60 and 0.6. So once you've graphed all the points, you can connect them. We can label this, because if we had multiple of them, we could say, okay, this is carbon dioxide. And we need a title, so we can say the effect of our independent variable, so temperature, so the effect of temperature on our dependent variable, which is our solubility of CO2. Okay, and so we've got our graph here. So your ticket out the door is graphing your own thing, so you want to make sure we look at how to create a graph and what those values mean.